In this video, we're going to look at gradients, divergence, and curl. So the question says if phi equals x squared y z raised to power 4, and we also have a vector function a equals x z I minus y squared j plus 2x squared y k, and it says find the gradient. This is the gradient function, so we are going to find the grad of phi, the gradient of phi, and we are going to find the divergence of A and the curl of A, which is vectors. So first, let's look at the gradient. We have grad phi, which is an expression for the gradient is simply partial si plus partial y j vector plus partial k or partial z k in a vector times phi, which is our function, our scalar function. So we are going to impose this condition on phi. So we have partial phi, partial si plus partial phi, partial yj plus partial z, partial phi k. These are just unit vector ijk. They are unit vectors. So our phi, which is our constant function, is x squared y z raised to power 4. So we substitute it here. We have x squared y z raised to power 4, the I unit vector plus partial y x squared y z raised to power 4 plus partial z x squared y z raised to power 4. So now we differentiate our constant function with respect to s for the height component. So we obtain 2xy z raised to power 4 I unit vector plus we differentiate our constant function also with respect to y. Doing that, we have x squared z raised to power 4. There is j unit vector here, j unit vector plus the third component. We differentiate with respect to z, so we have 4x squared y z raised to power 3. So that's our gradient function. So we have grad phi. Next thing is to obtain our divergence, which is divergence of our vector function, which is this. So in doing so, we have type A. Recall that grad, which is our gradient, is the same thing as this expression. So we write it here. We have partial si plus partial yj plus partial z k. Our vector function, which is sz I minus y squared j plus 2x squared y k. So we impose this condition again here. We have this is just a scalar function. We have dot product here. So each component we had on this. So doing so, we have partial s. Recall that I dot I is simply 1, because in dot product we have if we have an expression like a dot b, we are going to write as magnitude of a times magnitude of b times cosine of the angle that lies between a and b. And this is I and I, they are parallel. That is, we have I and j components. We have I here, we have j, and we have k. So I acting on I dot I, it is parallel, so the angle between is 0. So we have magnitude of 1, which is unit vector magnitude of 1 called 0, which is simply 1. So doing the same thing here. I dot j is 0. Likewise, k dot I is 0 because they are perpendicular to each other. So now continue with our expression. So we impose partial s partial. On this component we have sz. Since I dot j is 0, all this will just vanish. So we are going to left with I dot I. The same thing here, we have partial y into this. That will be minus y square plus partial z into 2s square is gate component 2s square y. So now we differentiate. With respect to x, we have z here. With respect to y, we have minus 2y plus. With respect to z, we obtain 0. So our divergence is simply z minus 2y. Now, to solve the third question, we have called A, which is cross product. So we can rewrite it as this. We have I, J, and K. So we have I, J, K. Yes, and our gradient, which is graph, is partial S, partial Y, partial Z. And our vector function, which is this, we have xz on the ith component and minus y square on the j component and 2s square y. So now we can impose the condition of vector product. This is simply plus minus plus. So in which we have plus I into this. We are going to fix the first row and the first column. First row and first column. So we are left with partial y of 2s square y minus partial z of minus y square minus j components. We have fixed the first row and the second column. We have partial s of 2s square y minus partial z of xz. So we have that. Now plus k, which is unit vectors ijk. So we fix the first row and the third column. We obtain partial s of minus y square minus partial y of xz. So now we can now simplify. Differentiating y with respect to 2s square y with respect to y, we have I into 2s square. Differentiate with respect to z here, this is just y square. Now is 0 minus j into. We differentiate this guy with respect to x, we have 4sy minus. We differentiate this guy with respect to z, we obtain x. So now for the kth component, we have differentiate this guy with respect to x, we have 0, since y is a variable or constant. So differentiate this guy with respect to 0, which is xz, we have 0. So we are left with 2s square I minus 4s yj plus 0. So our chord is 2s square I minus 4s yj. So that's the relationship between the gradient, the divergence, and the chord. Thanks for watching.